Hi everyone, I'm Avinaya Tripathi, a PhD student at Arizona State University, working under the supervision of Dr. Narayan Nethilath. Today I'm giving this presentation in behalf of Dr. Barzan, who I think is here. Yeah, okay. So my major focus is on 3D concrete printing, and this project deals with how we can modify small things in printing and with similar mortar mixes get better responses, because in literature we have been talking about printed elements being weaker than casted, right? So what are the ways we could most probably have those effects reduced? So I know, like in ACI, people have seen 3D printing a lot this time. So basically it's a construction procedure where this has got traction because of the ease of forming different very weird type of structures which you would have to construct molds for it. So the ease of doing it and sustainability aspect of it, because of lesser material being used, the lesser use of manpower, lesser use of wastage of material, has given it a lot of traction. And there are a lot of printing procedure, a lot of printer types. So the one we have in our facility at ASU right now is a gantry printer that has a capacity of doing a 1 by 1 by 1 kind of element in meters, basically, not in inches of it. So this is a picture of the gantry printer that we have. So in printing, usually conventionally when you see printing, unless required by the structure's modification, like if it's a curved edge or something like that, then only we tend to curve the filaments. Neither then we usually tend to print straight elements as far as possible. So what that does is, like usually in higher layer heights, we see that there is a chance of formation. This basically happens mostly if you have a circular nozzle. Now again, circular nozzle is advantageous because if you have a curving surface, if you use a rectangular, there will be twisting of filaments, which at least in circular you not see. So it's advantageous in that respect, but again, because of the circular nature of the nozzle, you will have curved edges resulting on voids, which again now is detrimental to the element. So why just stick with a straight element? Why make these voids so aligned in a line that we get a very weaker element from the mortar? So can we do small changes maybe? So what we tried is, like, let's not do a straight filament. We'll do it to compare, but again, let's change it. Maybe we can curve it. So what kind of curves could we do? We could have optimized it, but again, through smaller optimization, we tried two different types of print. I'll talk in detail about this one in the next slide. One modification could be that, like we could print a different way. And what can be the next modification? So this basically is because of the effect of filament shape and the filaments on top of two layers. So why print the next layer just on top of the lower one? Why not stagger it such that the printer pushes out more material, resulting on this void most probably getting removed from the system itself? So next thing we could do is stagger. And obviously a mortar is always weak in tension. We can just add fibers to the mortar to make it more stronger. So the three filament types that I talked about before that we tried are these three. I call this a linear filament, this is a S-shaped, and this is a 3-shaped. It does not look like 3, I guess, but again, that's the closest I could think of. So these are the parameters. We didn't play with the parameters here. We just wanted to play around with the way we print rather than playing with layer height effects. We have seen that there are layer height effects in the printed specimens in different works, but this was basically for a certain kind of parameters. We didn't change with the play around with these parameters. So for the linear type, we printed a linear conventional. This is usually what you will see done in industry. Real work, like in research work or wherever you see, this will most probably the one that you'll see. So the other model will be staggering the layers. You can see that the filament edges, you can see they are like aligned in a line. Well, here they are staggered, like half a filament. Similarly, we did the same model for S-shaped. For the 3 model though, we didn't do staggered, because in conventional, when printing this element itself, we figured out that because of the sharp changes on these notches, the filaments were not exactly 3, like there were more material being deposited on these edges. So we didn't think it was a necessary one. So we did do this and we compared the result for this, but we didn't go further for the staggering part. So we did some compression test also on this, but for the sake of being shorter on my presentation, I am just going to present my flexure results here. So we did a lower fiber doses initially. So for a usual motor mix that we have been printing at ASU, a 30% replacement of limestone of cement by limestone, and a 50 by mass of sand and binder. So this is a typical mix that we use at ASU. What we did on this was we tried two different fiber types, a steel fiber and a basalt fiber. So the steel fiber, I should have put a figure, I forgot to put that one. So steel fiber are in the range of the fiber we used were 0.2 mm diameter and 15 mm length, and the strength that it could sustain, tensile strength, was 3 GPa, while the basalt fiber was about 10 times smaller in diameter, about 0.04 mm diameter, while the length was 15 mm itself, but the strength again a 10-fold decrease at 0.3 GPa. That will come into consideration later, because with 0.3 and 3 being the strength, there will be something that we saw that is quite fun to see. So from the slabs that I showed before, we cut out 60 by 60 by 300 mm beams, which we subjected to 4-point bending, and here I'm right initially just presenting the non-fiber mix. So this basically deals with change of geometry from linear S to 3, and this deals with change of layering type from conventional to staggered. So the first letter represents the type of filament, and the second letter represents the type of layering here. I should have described that before, but so what we could see here right away is just by changing the type we print, the filaments type we print, the motor is the same. Basically nothing changed, just the way we shaped the filament changed. We got about 33% increase already in flexure strength. So that's a very good advantage. With same motor, same print times, everything remaining the same, we are getting a 33% better response in flexure itself. So now these three also perform quite well, about 25 to 30% increase. Again, for the reasons that I told before, we didn't continue with those filaments. While we staggered the filaments, again, with compared to conventional, we can see that the linear stagger itself performed as good as a S-shaped conventional. When S-shaped again was staggered, there was even a further increase in flexure strength. So from a conventional type of print that we do to a S-shaped staggered, we are already about 30, 40, 50% of increase flexure response. Now, what would fiber do in this? So the base model that we had before, the linear staggered and S staggered, we introduced the same model with steel fibers and basalt fiber to see what the fibers will do. We can see that fibers did increase the strength. From the model that already had 40 to 50% increase in flexure strength, we are seeing a further 30 to 40% increase in the flexure strength just by introducing fibers. A thing to note here will be like S did perform better when there was a non-fiber mix, but now in a fiber mix, the linear model performed better than S-shaped mix. This is basically because it has been established in literature quite well that the fibers tend to align in the direction of print. So the linear print having the print direction along the length of the beam resulted on more fibers being aligned along the length of the beam. So basically giving it a better crack maintenance capacity with the fibers being aligned on the line. While for a S print, again, the direction does not technically, for two portions of it only, it aligns along the length. So most are angled at 4 to 5 degrees from the length of the beam, resulting on lesser increase in the flexure strength. So this is the flexure strength response that we got for the beams. I think it was a discussion in yesterday's committee too that, okay, we can't get this post-peak response in beams, usually non-fiber beams. And it was the same case. This is a representative figure among the 6-7 beams that we tested. 1-2 showed us post-peak response while most did not. The major things we could see here is like the capacity, not only the capacity, but the stress capacity, but the strain capacity also is increased because of the change in geometries, change in layering style. We are getting into higher flexure strain without fibers also. With fibers, basalt gave us a higher strength beam, but gave us a more brittle kind of beam, like it did not allow it to attain higher flexure strain. While with steel fiber, though we got a lower flexure strength, we got a more ductile response, so giving it more toughness. So basalt fiber giving us more load carrying capacity, steel fiber gave us more energy dissipation capacity. Again, DIC was also used to check the strain profile on the beams. So it again correlated the same response that we saw on the flexure stress strain response, being the linear conventional showing a lesser strain at peak, while the modified beams showed a higher strain capacity at peak loads. So now that was with a low fiber doses. Okay, I forgot to mention that, I guess. It was a 0.28% volume by fiber for both the steel and basalt fiber that I showed before. So that was now a lower volume percent. Why not try a higher volume percent? The biggest problem while trying a higher volume percentage in 3D printing will be clogging of the nozzle due to those fibers. So what could be done? So we had to modify the mix such that we have it viscous enough initially when rotated by the extruder, but again stiff enough that once it is extruded out of the nozzle, it needs to sit stiff. So while we are changing it, we are using SP and we are trying to reduce water cement ratio. So why not try to get a USPC out of it? So everybody who has seen a USPC will think like USPC flows, right? So that's how we usually make it for a cast purpose, for the ease of work. But for a print now, we can't have that. If we have something flowing, nothing is going to stand. We can't print at all. So we had to modify the USPC mix again to make it this print that you see on the right. This is a wall and a cylinder print. Some people might have seen my other 3D printing presentation. These are the wall and hollow cylinder that I use for buildability validation. So I did the buildability validation for this also, and it did stand correct. And this is just 15 minutes after the mix. So you can see with the USPC mix, it need not be flowable for the printing. We could print it. So now here I tried 3 different mixes. I'll talk why I didn't try a basalt fiber 1%. We initially started with a steel fiber 1.5% by volume and a basalt fiber 1.5% by volume. We didn't try basalt fiber because now it was weaker, that will come later. And we tried a steel fiber 1% and again a plain without a fiber mix. Oh, and to just clarify, for this, it's just a conventional print that we did. We didn't do the modification. So all the strains that you'll see will be for a weakest of the before that you saw. So just for a revision, this was the flexure strength that we obtained before, highest being around 4 MPa for the normal mix that we got before. So here, this B part shows the printed flexure strength for the printed beams, while this is for the casted beams. You can see that the weakest non-fiber mix itself has a strength of 4 MPa, so it's equivalent to the best that we had before with fibers. Again, because of the low water cement ratio, the mix being UHPC and all those. So from the casted, again, before I didn't show that for the other mix because it was not important, because okay, casted was always better than the printed. Here the casted is important to be seen that because of one single reason. You can see that all the other 3 are weaker for printed, but for 1% steel fiber, we saw a better strength in the printed sample rather than the casted sample. So why is it that so? That again boils down to fibers being aligned in the direction of the print. So it's a linear conventional print again. While casting, the fibers are randomly oriented. So there's not enough fibers. So the black is the flexure response for the 1% casted fiber. There are not enough fibers aligned in the length of the beam that it gets a strain hardening effect. There's a slight, but not much. But for printed, because most of the fibers are aligned in the length of the beam, we saw a strain hardening response, resulting in a higher flexure strength achievement. So now there's something anomaly. Something printed became better than a casted. So maybe we could use the fiber orientation in printing for our advantage. Maybe we can orient the fiber filament such that wherever we need the strength, we just orient. Let's say we want a truss, we want a tensile compressive response, right? So rather than being it randomly oriented, if it is oriented along the length, it will have better response. For a 1.5% fiber, again a higher fiber percentage, the casted one performed good enough, better than the printed one. Here again, most probably it boils down to a certain percent. There's an optimized percent where printed with fiber should most probably work better because of higher. It's basically around the range where it shows strain hardening. So once it shows strain hardening for the casted, it will most probably be better than the printed. With basalt fibers, with previous beams, at least some of the beams of the 6 showed a post-peak because this is a high strength mix. At the peak, there was no post-peak response. All the beams broke. At this, we tried our best to maintain the deflection rate, but again, we saw that beams at the peak load just broke apart, being brittle. So basalt fiber just allowed us a higher load carrying capacity without any ductility, while for steel fibers we can see there's like a very large post-peak response that we can get. From the peak, this is at a very high strain rate. I had to stop at this point because it was a very long test procedure and the load carrying capacity is still way beyond 50% of the top, like the highest peak load capacity. So with 1.5%, we are getting a very good toughening effect of those. So these are some of the conclusions of the stress strain response that I was just talking about, like 1% outperforming the casted, 1% is still fiber providing high ductility and all those things. Again, DIC for this was also done, and similar thing, we saw similar response. It was just to check that how strain is there. So this boils down to another part of the project that we have not done it. We could most probably start tracking the crack mouth opening, seeing how the crack propagates, which we have not done right now for this project. We are just doing cross-check with all the strain results obtained from an experimental test to DIC results. Do they show similarity? Like this is a plain mix versus basalt mix. We see that the strain at peak load are higher for the basalt mix than a plain mix, which was seen in a flexure response also. So as a conclusion of the whole project that I showed here, basically we can see that mechanical response of 3D printed elements could be enhanced just by minor changes to it. Maybe this is not the best change. Maybe there's a more optimized way of doing it. So these minor changes need to be revised. Like people need to try to see if there are some changes that could be made to get a better enhancement of the response of a 3D printed element. Again, short fiber concrete mortar used for printing helps enhance mechanical response, which obviously we'll think as such. Again, when I say mechanical response, I have an asterisk here, which while I didn't show the compressive result that we have. So for lower volume percentage, we didn't see a compressive strength increase. With basalt fiber, we even saw a reduction in strength for the compressive strength. So it does not mean all the mechanical responses will be increased with fibers, but maybe for a particular purpose that we are using, a particular response that we want to enhance at higher percentage compressive strength for steel fiber increase, where basalt fiber again decrease, but we could most probably use in that sense. And again, in print rather than casted, the tendency of the fibers to oriented along a direction of print could be most probably used as advantage for optimization purpose and stuff. With that, I like to acknowledge NSF and Department of Energy for their funding, and my senior Suraj Nair for all the motivation and all the counseling and everything he has done for me throughout the PhD process. Any questions?